All right, exciting as all this politics talk is. Good morning, everybody. Welcome back to Math 105. Plan for today is we are going to finish off Standard 14, and if we have time towards the end of class, start looking at Standard 15 and start talking about triangle congruences. As far as office hours go, got my usual office hours. Today at 10 in the morning, 2 in the afternoon, tomorrow at 10 in the morning, 1:30 in the afternoon. And as far as homework goes, Standard 14 quiz is not available yet, but will be after all my classes today, and that will be due on Friday. Just to give you a sense of where we're going, I'm planning on doing an exam next Friday, I'm currently thinking. Standard 15, because, and the third exam will be over Standards 1 through Standard 15, be very similar in structure to the standard, or to the exam 2, which is just over 1 through 10. But it'll be the same deal. You'll get to choose six standards out of the 15 available, and pick whichever ones you want / still need. And I'm not exactly sure about the date of the exam. I'm currently thinking next Friday, but also kind of depends on how class goes today and Friday. But that's currently my thoughts. Any questions or comments before we get started today? All right, a statistics professor distributes a 50-question true-false test. During the exam, the professor notices that one student, just sitting in the very back of the room, is going through a pattern of looking at the exam, flipping a coin, then picking an answer after seeing how the coin falls. This goes on for 2 full hours, and after all the other students have left, that one student is still back there flipping a coin, looking at the results, and filling in their answers. The professor goes up to the student. Listen, she says, I know you aren't prepared for the exam, and I know you've been flipping a coin to determine the answers, but what I don't get is, what could possibly be taking you so long? The student glares at the professor and says, shh, I'm checking my answers. Okay, so last class we went through and discussed Proposition 2 from Euclid's Elements, which is the proposition that says, given any point, A, and any line from B to C, that doesn't include the point A, it's always allowed / possible to construct the line going out of A such that this new line going out of A is equal to the line BC. And we proved that using a bunch of shenanigans involving, we used Proposition 1, in which we started by assuming we could draw equilateral triangles, and then we drew a bunch of circles in order to get to our results. And today, I want to start class off by looking at Proposition 3, which is going to say, given 2 unequal straight lines, it's possible to cut off from the greater a straight line equal to the less. So we touched on this last time, but what that meant is if we've got a nice long line here from A to B, and a shorter line, which the proof is just going to call line C, there should be able to find a point on this line from A to B. It'll be about here-ish, such that the length of the segment from A to this new point, which we're going to eventually call E, is equal to the length of the line C. And in order to do that, we are going to, along the way, have to rely on proposition number 2 in order to say we could take our longer line and cut it off at a point here, E, that has, so that we're cutting it off at a point so that what's left is equal in length to this other shorter line that we started with. So let's see if we can do this. So go ahead and erase the E because we'll be finding it along the way. So to start things off, we're going to let AB and C be the two unequal straight lines. And let AB be the greater of them. Euclid uses some kind of weird notation here, I think, in that in every other example before, anytime he drew a line, he always kind of gave variable names to the two endpoints of the line and then said, this is line BC, this is line AB. I don't know why Euclid did it this way, but in this case, he's only specifically going to give a name to the line as a whole and say, I'm going to name this line C, rather than what he would typically do and say, I'm going to call this point C, this point D, and then call the line CD. Instead of naming the points at the either end of this line, he's just going to call the entire line C. And maybe at the end of our proof we'll talk about why that is. Why didn't he give names to the endpoints? Any questions or comments before we get started with our main bulk of our proof? In that case, we're going to say thus, it's required to cut off from AB a straight line equal to C. By which we mean find a point on line AB such that the line from A to this new point is equal to the line C. So right off the bat, the first thing we're going to do after setting up everything is we are going to use proposition number 2 to say that at the point A, we're going to let a line AB be placed that is equal to C. So right off the bat, Euclid's saying pick some point D, let's say about here-ish, and a little bit longer. Here-ish, such that the length of the line going from A to D is equal to the line C, meaning the length of this line from A to D is equal to the length of this shorter line C that we started with. Proposition 2 is going to be what allows us to do this because it's proposition 2 that says, given any point here A and any line that doesn't include A, in this case the line not including A is going to be the line C, we can always construct a line starting at A that has the same length as C. So question. Why couldn't we have just picked our point B to be the point right here, and then we'd be done right away? Why can we not necessarily say that just pick our point D on the line AB and say, boom, done? Because in particular, it's something to do with the way proposition 2 is worded. That's going to tell us something about why can't D be placed right here necessarily.
Is it because he says at a given point?
I think that part's okay. I think here we can just say A is our given point. And he says at a given point. He just means you need to specify which point you're talking about, but it could be any point in the plane.
doesn't he say something like a new straight, or to produce a new line or something like that? He basically, he's something in the words like a new line, and it implies that it's unique, that it's a different one.
A new line. Okay. Let's see. Could be. I think there's certainly. I don't think the line going from A of this length has to be unique. Here's my proof. Boom! I just found another one. So I don't think necessarily that. I think you're close, but it's not that this line right here from A to D has to be unique as such. If it is unique, then we're in trouble because we need to find another one that'll be here. Any other ideas? I think the reasoning ultimately comes down to the fact that in Proposition 2, Euclid doesn't specify when it says when we can place at a given point a straight line equal to a given straight line. This new straight line we're creating, Euclid doesn't give us any guarantees about which direction that line points. He says, at the point A, we should be able to produce a new line that's equal to this line C, but we can't. But Proposition 2 doesn't tell us that we can make that line point in any direction that we want it to. If you recall, in our picture from Proposition 2 yesterday, the line BC and the line AL that we found ended up pointing in slightly different directions overall. And so I don't think from Proposition 2 Proposition 2 allows us to find a point D such that the length of this line is equal to the length of C, but it doesn't necessarily, as written at least, tell us that we can pick our point D to be any direction we want, say, in the same direction as B. If it did, that would be great, and then Proposition 3 would be extremely quick to prove. But it's not quite that easy. So next up, now that we have a point D, we're going to make a circle. So, and with center A and distance AB, let the circle DEF be described. So I made a circle that is centered at the point A and whose radius is equal to the length of the line from A to D. And he said call the circle DEF. F's not going to matter. I'll just put it down here. E we're going to specifically be the point that lies on the line from A to B. So this will be our point E right here. So just looking at this picture, what do you all think? I think we can find right away, I think we can see, just looking at this picture, the line we're looking for. A line that happens to be cut off from the line AB, but a line that's going to be equal in length to this line C up here. So which 2 points, the line between which 2 points in this picture is both going to be cut off from the line from A to B, and also is going to have the same length as the line C, do you think?
AE.
It's going to be AE. And that's ultimately going to come from the fact that, by definition, the distance from A to E has to be, or the line from A to E has to be equal to the line from A to D, which in turn is equal to the line C. So common notion 1 is going to tell us AE also has to be equal to C. So just to write that all up, I'm not gonna keep doing the big guessing game of every time we draw a circle from here on out. I'm not gonna keep asking the question which postulate allows us to draw circles, because I feel like I've asked that enough times at this point. But it is still useful to keep in mind postulate 3 is what tells us we are allowed to draw our circle centered at A, whose radius is equal to the length of the line from A to B. So since A is the center of DEF, AE equals AB by definition 15, where definition 15 is again just the definition of circle, saying since AE and AD are both lines going from the center point to a point on the circle, these two lines are equal, according to Euclid's definition of a circle. But C is equal to AD2, thus each line AD and C equals AD, or excuse me, AE and C equals AD. So that also AE is equal to C. And which postulate slash common notion is going to tell us here that since AE and C are both equal to AD, AE must equal C?
Common notion 1.
Good old friend, common notion 1. Things which are equal to the same thing must also be equal to each other. Is there anything surprising to you in kind of the wording here of how Euclid uses common notion 1? Because we noticed something the other day about how Euclid kind of specifically kind of used common notion 1 in propositions 1 and 2 that isn't happening here. How is his, or at least the phrasing of the proof here, a little bit different from how he used common notion 1 in the last two proofs?
Well, he doesn't take the time to write out common notion 1 completely like he did in the others.
Yeah, surprise. He's, for once, he's actually okay with just saying AE and C both equal AD, therefore A equals C. He's not explicitly saying because things which are equal to the same thing must also equal one another. Didn't do that here. Good for you, Euclid, in my opinion. He does do that later in the elements still, from time to time. So A equals C, and then we're basically done because we can just say thus, given the two straight lines, AB and C, from AB, AE has been cut off equal to C. QE. Any questions or comments about this proof? So, quick question, what I didn't include in the packet, I forgot to include in the packet. Why do you think Euclid didn't give endpoints to, why do you think Euclid just called this line C instead of giving it endpoints? Like, I'm going to call this point C, this point D, refer to that, and then refer to the line as CD. Any ideas why Euclid just said, I'm just going to call the whole line, give the whole line a single variable name, and why he didn't necessarily need to give it the two endpoints names?
The random shot. Is it because it kind of just exists to be duplicated, so we're not going to be spending a lot of time focusing on it, and so using a lot of variables on it would kind of detract from what's going on with the rest of it, with the rest of the stuff down there.
I think I would agree. I think Euclid decided he doesn't need to ever specifically refer to the endpoints of the line, since the only thing he ever does with this line, like you said, is just to immediately duplicate it down here, so that we get the same line starting at A. And the duplication process is just something we automatically get from proposition number 2. So the fact that Euclid, so the fact that we had this line, we didn't ever really need to refer to the endpoints in any way. We didn't do anything like construct a circle around on it or anything like that. And so I would agree that I think he's just trying to keep it simple and reduce the amount of variable names that he uses overall. He certainly could have, and then just made this CD, this E, this F, this G, and the proof would have worked out the same way. But he just decided, I guess, I don't need it. I don't need names to be endpoints, so I'm not going to use them. So, one last question that I have for you all in this packet. Do you think that the order in which Euclid proved his first 3 propositions mattered at all? Or could he have done proposition 3 first or 2 first, or done like a 1, 3, 2 sort of thing? Or did it have to be this specific ordering for the first 3 or not postulates? One of these days I'm going to learn the difference between a postulate and a proposition. First 3 propositions.
It definitely does matter because he uses the first and then the second, and the second proving the third. It's cumulative.
And so we wouldn't have been able to start with a second because he would have had to rely on something he hadn't proven yet.
Right.
That sound fair to you all? I would totally agree. I think the order in which he proves the propositions is very important to some degree, but especially for these first 3, in that he can't use a result he hasn't previously proven. So the order of propositions 1, 2, 3. Answer is it totally mattered because he used proposition 1 to prove proposition 2, and proposition 2 to prove proposition 3. And a general good rule of thumb is you can't use a result, you can't use a proposition unless you've already proved it. And this is going to be something that Euclid is very careful about throughout the Elements, in that he specifically orders all of his proofs in a way that he never has to rely on a proposition that comes later on in the Elements. Anytime he cites the result of a proposition, it's already going to be something he's proven. Which also, by the way, is related to the reason why do the common notions in postulates come before the propositions. It's because he wants to be able to call on the common notions and call on the postulates, and he can't do that unless he's already stated those previously. Euclid's never going to say, in this proof of the proposition, I'm going to call on postulate 5. What's postulate 5? Don't worry, I'll define it for you 20 pages from now. He's always careful not to use a result unless he's already stated it, and if it's a proposition, unless he's already proven it. That doesn't mean every proposition has to be in the exact same order going on. Proposition 4, for instance, which we're going to look at next, doesn't rely on the first 3 propositions at all. So it could have gone in any order. It could have come first, it could have gone second, it could have gone third. But if you have a proposition like number 2, for instance, that relies on a different one, in this case number 1, proposition 2 would have to come after proposition 1. Any questions or comments about that? Okay, so that in that case, that is going to do it for our standard 14 packet. Because the last question we had already talked about in the previous class on that back page. So next up, I want to talk through standard 15. In which standard 15, we're going to start going out of order a little bit. Let's see, we're going to talk about propositions 4, 8, 26, and 6 in that order in the new standard. There's a new standard packet by the door, if you'd like it. And in this standard, what we're going to be focusing on is triangles. And specifically, the idea of what does it mean for 2 triangles to be equal? What are some ways in which we can prove that 2 triangles are going to be equal / congruent to each other? So let's say I drew out 2 triangles. Pretend I drew these better so that they're the same size. Actually, you know what? I'll just do it. I would argue these 2 triangles are congruent to each other. What would you say makes these 2 triangles equal or congruent?
Well, to the eye, it looks as if the sides and the angles within them are the same.
The side lengths are the same and the angles are the same? I think that's a good way. I think that's a great way to define what does it mean for 2 triangles to be equal. If all the side lengths are the same, how do I do this? This one, and all of the angle measurements are the same. So we want to make a comparison between side lengths. For instance, which side in the second triangle would you say that AB looks to be equal to?
EF.
EF. Good. That's what I intended with my drawing. BC. ED. Yep, kind of the diagonal one. And then AC and DF are going to be equal. So the sides are all equal. And also the angles are equal. The angle at A is going to be equal to the angle at F. The angle at B is equal to the angle at E. And the angle at C, kind of the smallest angle, is going to be equal to this angle at D here. So we could say triangle ABC is going to be equal to the triangle at DEF because all sides and all angles. are equal. I think that's a solid choice of definition for what it means for two triangles. I'm not, however, convinced that's the definition Euclid would use.
I think you missed the dash through ED. It only has one.
So I did. Good catch. How do you think Euclid might have defined triangles being equal, if not for all sides and angles are equal? Based on kind of the ideas that we've seen in previous standards of how Euclid interpreted lines and angles to be equal to each other. What are your thoughts on how he might interpret triangle equality?
That it could have to do with combination of all and them being able to coincide with one another.
Yeah, something about you could pick up this triangle, rotate it. You'd sort of need to do a reflection, pick it up and then flip it around this way. But then you could put it right back on top of the other triangle in a way that would cause everything to match up. I think that's how Euclid would define it. Two triangles are equal if they can be made to coincide. And so, what we're going to be looking at throughout this standard is we're going to be looking to answer the question of how can you show from a minimal amount of starting information two triangles have to be equal to each other. If we go through the definition of all the sides and all the angles are equal versus just the definition of they have to be made to coincide, what is sort of the smallest amount of information that we can start with that would allow us to actually go through and say this triangle has to be equal to this triangle without necessarily knowing from the get-go all three sides and all three angles are equal to each other. Any questions or comments? Okay, so first proposition we're going to be looking at related to this is proposition number 4. I need to get some new chalk for my next class. There's some skimpy pieces. Where proposition 4 is going to say if two triangles have the two sides equal to two sides respectively, and have the angles contained by the equal straight lines equal, they will also have the base equal to the base, the triangle will be equal to the triangle, and the remaining angles will be equal to the remaining angles respectively. Namely, those which the equal sides share. Okay, let's draw a picture, see if we can try and interpret all this, because this is a bit of a lengthy proposition. So the idea here is we have two triangles that we want to show are equal. We'll label them as such, ABC and DEF. So what we're going to assume is we know two sides are equal to each other. I'm going to assume side AB is equal to the side DE. And AC, I'm going to assume, is equal to DF. And then we're also going to assume that the angles contained by these two straight lines are equal to each other. So the angle at A, we're going to assume, is equal to the angle at D. According to this proposition, if you know we have two pairs of sides that match up, AB and DE, AC and DF, and if we know that the angle between those two equal pairs of lines are also equal, according to this, that's going to tell us the bases have to be equal, the remaining angles have to be equal, and the two triangles will have to be equal to each other in the sense that we should be able to pick up one triangle and have it coincide perfectly with the second triangle. Pop quiz from high school geometry. What's that? I just heard you say the word side and or angle many times.
Those are all different ways of proving if triangles are congruent.
These are all different ways of proving different triangles are congruent. Which of these is the proposition going to be referring to? Side angle side? Indeed. Basically, this proposition 4 is the proposition that basically tells us side angle side works out. That if you have two triangles and you have two pairs of sides that are equal, and the angle in between those two sides are also equal, then the two triangles have to be congruent, meaning all the sides match up, all the angles match up, the life is hunky dory. Yeah, that's exactly right. And these others are going to be other propositions in the elements. I decided for the proposition 4, I wasn't going to write out the whole thing on the board and go through each step painstakingly because the proof's kind of lengthy. So I thought what we would do instead is just kind of talk through the proof. I typed it out, it's in the packet, it kind of goes both from this page into the next page. And I thought we could just kind of talk through each step without having to necessarily write it all out in gory detail. And we're going to be doing that with a lot of the propositions going forward, is we're just going to be looking at the proof instead of writing it all out ourselves. I wanted with the early propositions to kind of write it all out so we can kind of talk through how to construct it as we went through the proof more carefully. Now that we've kind of had a standard and how to do that already, we're going to go through these a little bit quicker. So let's see what the proposition 4 says. So to start off, we're going to assume we have these two triangles. ABC, DEF be two triangles with AB equal to DE and AC equal to DF, and the angle BAC equal to the angle EDF. So basically, the first paragraph of the proof, suppose we have these two triangles that I just drew out on the board. I say that the base BC is also equal to blah, 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 thus now he's establishing everything he wants to prove. I didn't want to spend 10 minutes just writing those two paragraphs down because I basically kind of already did with the picture and state of the proposition. We're going to prove these triangles are congruent. So starting in paragraph 3, right off the bat, Euclid is saying, if the triangle ABC be applied to the triangle DEF, and if the if the point A be placed on the point D, so he's talking about placing the point A on the point D, and the straight line AB on DE, then B will have to coincide with E because AB is equal to DE. So in other words, if we were to just take this top left line, making up this triangle, Euclid is saying, since we assumed AB as a line is equal to the line DE. What Euclid is saying is that if we were to pick up this line, AB, scooch it over, and place it on top of line DE, then since, or at least place A on top of D, since A is being placed on top of D and AB is equal to the line DE, Euclid claims B is then going to have to land right on top of E. So ultimately, Euclid's trying to make a proof here where he's talking about how you can place one triangle on top of the other, and he's going to go through an argument to show that, that these two triangles would have to match up. So from the get-go, if he tries to lay this first on top of the second, he's placing A on top of D, and then he's saying B will have to match up perfectly with E, because these two sides were equal. Again, AB coinciding with DE, the straight line AC will coincide with DF. So now he's saying this line from A to C will have to match up with the line from D to F. Why? Because the angle BAC is equal to the angle EDF. And so the point C is going to have to match up with the point F, because these two sides are equal. So in other words, Euclid's taken this first triangle, placed it on top of the second, and these two sides matched up from A to B versus D to E. Now he's saying, since these two angles are equal, and since side AC is equal to the side DF, where AC ends up getting placed is going to have to match up with where the side DF is going to be placed. He doesn't explicitly say so, but he's making heavy use of that common notion number 4 here, about things which are equal will have to coincide. But B coincided with E, hence the base BC will coincide with the base EF and will be equal to it. So in other words, B matched up with E, C matches up with F, therefore Euclid is saying that the straight line for B to C will have to match up with the straight line going from E to F. This time, not from common notion 4, but from postulate 1. I totally wrote common notion 4 here. Well, you can think about it from common notion 4 or a postulate 1 standpoint. Common notion 4 standpoint will be, well, you're placing these 2 points in the same place, you're placing these 2 points in the same place, so the line between them will have to match up entirely as well. Thus, the whole triangle ABC will coincide with the whole triangle DEF and will be equal to it, and all the remaining angles will coincide and be equal. Everything's hunky-dory, QED. Here's my question. It may shock you to learn that modern geometers have found this one to be a bit controversial. The proof of this postulate, side angle side. Why do you think they might find this to be a controversial proposition?
Well, it's based on something that is controversial, mainly that the ability to pick something up and place it over top of something else once it's on the page. Geometers, I remember you saying, don't really like that. The idea that they're just able to, you're able to move stuff around once it's on the page and make it coincide to make your proof work.
So in other words, you're saying that our proof kind of relied heavily upon common notion 4. And as we said before, common notion 4, the idea that, oh, if 2 things are equal, you should be able to pick one up and put it on top of the other, was a controversial one?
Yeah.
Absolutely. This is like, the entire proof is basically just saying common notion 4, common notion 4, common notion 4, over and over again. is because, I said, heavily relies on this common notion number 4 and the idea of being able to move around and coincide triangles. Which feels very imprecise to a lot of geometers. What do you all think, though? I'm curious to get your opinions on this proposition 4. So you don't have to agree with the geometers. You think that this works, that what we just described, the process I described, works fine as a proof? Assuming, you know, I had written it out instead of just kind of talked through it?
Kind of language that he uses, like, when he says you move them to coincide, you already assume that they're congruent when you said that the two sides of the angle were congruent, and then he's just saying, like, because they're congruent when you put them on top of each other, they'll coincide. He doesn't need to say that, it's kind of like the language that he uses.
And it's just, you're moving on top and they will have to coincide. So you're kind of sounding like, yeah, you don't think it's very precise sort of language?
I mean, no, I think it makes sense, it's just, well, yeah, I guess the language he uses is confusing, but.
But the idea you think gets across just fine?
Yeah, right,
Okay, that's fair.
Yeah, I kind of agree with that. So from a precise mathematical standpoint, there are a lot of problems, but from, like, it's more in like applied mathematics, it makes sense. Like logically it makes sense. We know in the real world you can do that with objects that are exactly the same on top of each other. They're gonna line up exactly their sides and their angles. So I see how on the page it's a problem, but if we were to use this proof in everyday life, like perhaps in engineering or something like that, it would work out. It would work out okay in real life. So again, though, Euclid isn't really focused on real life. He's focused more on, you know, the pure mathematics. So from that form, this isn't really a pure proof. Yes.
So to an applied mathematician, that explanation you think would work out just fine. Yeah, sure. Things coincide, that makes sense. Sure, right? That's a result that we can use to do things with like engineering and such. But to a pure mathematician, it's a bit more problematic for trying to come up with a proof that just has this nice flow of logic to it.
Yeah.
Okay, interesting. Okay, again, I'm repeating everything. I'm just parroting back everything you say just so the people watching the video can hear it. Otherwise, I wouldn't have spent so long restating exactly the same words.
Would it be possible to use proposition 2 to map every line onto the other one? So draw a new line that's equal and pick one of the points to duplicate it onto, and then see that it lines up that way?
Interesting. Okay, so you want to try and make this like, you want to try and use this kind of from a different perspective, which is using a previously proven proposition, proposition number 2. Okay. I think you can get two sides to match up that way, but you're not going to get everything to match up exactly the way you want it. And the problem with that is because I know things you don't about what modern geometers have tried to prove this one. So we are out of time for today, unfortunately. I think you all have some very good viewpoints. When we come back on Friday, though, we will continue our discussion of Proposition 4, and we'll talk about how have the geometers who looked at this, who've mainly been pure mathematicians, what viewpoint have they taken to try and prove Proposition 4, and when that didn't work out, how to deal with it otherwise. But slight spoiler answer for next class. Modern geometers tried to prove Proposition 4 using previous propositions and found out that they couldn't. Hope you all have a good day. I will see you on Friday.